second talk of the morning, given by D.Karabas, IPMU. Topic is about Fukaya derivatives and quiver presentations.
Yeah. Okay. Thank you for invitation and introduction. So first I will give you the setting. So then I will say what kind of problems I think on that setting. Okay. So setting is, so let's take any symplectic manifold. So in this symplectic manifold, let's say we have some Lagrangians, C1, C2 to Cn. So some exact, so normal Lagrangians. So, and I want them to, let's say, intersecting transversely. So this Lagrangian intersect transversely with each other. And then from that information, you can create a quiver, right? Okay. Let's say get quiver from that. Just remembering how this intersection happening. So let's say, let me draw a picture. Let's say this form manifold, we are considering two-dimensional Lagrangians. I may mess up this picture, 1 second. Let's make it even more complicated. Let's say they intersect like this, and at here they intersect transversely, okay? And this is S2, 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 and this is R2, let's say. I mean, it can be anything, but let's say this is the example. And this is immerse, by the way. So it self-intersects once. So from this, you can get this quiver. For each piece, Lagrangian, you put a one dot. And just recall what they are, decorate them with what they are. And for each intersection, put an arrow. So there's an intersection between this, put an arrow, intersection here. So there are two intersections here. And one intersection there, this is R2. And one self-intersection, so self-intersection means loop. So I get this quiver. So what does arrow mean? So arrow, actually I should decorate with plus minus, but I will ignore in this talk. So this means intersects positively. This means intersect negatively. But let's assume everything is positive, just for the simplicity. So if I decorate like this, yeah, from this picture, I can get this kind of topological picture back. So direction of arrow is just to make this sentence meaningful. Because intersect positively, like you need first one and second one, right? First one intersect positively with second one. So that means this one intersect positively with that one. That kind of meaning. And that matters depending on dimension. Maybe intersect positively also, I mean, in the volume form coming from the symplectic structure, but yeah, so in the end, like there are two choices. Actually, there are essentially two choices here, actually, even with plus minus. So, I mean, in even dimension, the directional arrow doesn't matter, basically, in even dimension. So, then this is happening in symplectic manifold, right? So I take this Weinstein neighborhood. So take a neighborhood of that picture. And let's call it X. So I take Weinstein neighborhood of X. Actually, it doesn't depend on the ambient W. So this is Weinstein neighborhood theorem, and you can extend to this kind of pictures. Its neighborhood is standard. So I can just actually from this picture, I can get this neighborhood inside this symplectic manifold. And I will denote it like T star X, but with quotient, quotation, which means Weinstein neighborhood. It's because it's like cotangent bundle. If it is something smooth, the Weinstein neighborhood is like cotangent bundle, or this bundle, you can say. If something is not smooth, at singularity you need to do something, but it's kind of cotangent bundle of that picture. It says Weinstein manifold. It's a Weinstein manifold or domain manifold or sector. That means an exact symplectic manifold. With nice level vector field. Level vector field just escaping up this. And I will call it like plumbing. According to Q. And denote it like P and Q. And here refers to dimension of the space. And dimension of Lagrangians. Maybe, is it clear definition? So what do? I take this quiver, Q. From that quiver, I create that picture. So now I do the opposite direction. I start from manifold and get quiver, but now I can do it for any quiver. So I start from quiver, draw that picture, take the cotangent bundle, kind of, which actually Weinstein neighborhood of that thing. It gives you a new symplectic manifold. It's actually Weinstein manifold, which is a nice, exact symplectic manifold. And I will call it plumbing space. Okay. So goal is studying this kind of spaces. So go study this. Also studying this maybe will later help us to understand this any symplectic manifolds in some way. I mean. So I mean, it's some understanding this will be good information. Okay. So before telling more, I should remind you maybe Fukaya category, definition of Fukaya category of such symplectic manifold. Okay, wrap Fukaya category. Of a symplectic, a Weinstein manifold. So this W is now Weinstein manifold. So it's an infinite category in general. So objects and some exact Lagrangians inside W with you equip them with local system on them and more stuff, but I won't want to talk about them. And with cylindrical end means they are boring at infinity. They don't do much stuff at infinity. They just follow the level vector field. So this compact part is more topologically rich. But non-compact part also important, of course. So morphisms are, let's say, two Lagrangian. This just generated by, so this is like graded vector space. So since I said that, let's fix some coefficient field. So let's call it coefficient field, K. But actually, I can work with commutative ring. Just for simplicity, I'm choosing this. The results, I will say, most of them true for commutative ring. But some last one, the second part, I need for field coefficient. So these morphisms are generated by these intersections of that two Lagrangian. But you need to perturb first Lagrangian, perturb by Hamiltonian, which is quadratic at infinity. So at infinity, I need to perturb in a particular way. I cannot perturb with any Hamiltonian. Because, I mean, the infinity part is problematic. So to make a nice theory, I need this kind of condition. So this kind of condition calls it RAP. Like perturbing with that kind of Hamiltonian calls it RAP. Therefore, it's RAP Fukaya category. So, and infinity operations, you count holomorphic disks bounded by Lagrangians or homomorphic polygon, and you determine these infinity operations like mu1, mu2, mu3. Like mu1 is differential, you can think like this. Mu2 is composition, and rest is higher morphism. And if mu3, mu4 they are 0, then this is like DJ category. It's called DJ category. So I denote it like W Fukaya of W. And if I don't put W, that means I'm considering compact Lagrangians only. Okay? So objects, compact Lagrangians. And the rest is the same. So therefore, you can say this is subcategory of full and faithful subcategory of this. Compact, of course, compacts are everything. Okay. So any questions so far? This is Fukaya category, this is the setting. So now I will tell what kind of problems I'm thinking in this setting. Some vague motivation. Don't, like, let's say, first let me say, one is why I just introduce Fukaya categories and why I want to study this via this kind of invariant. First of all, this invariant itself is interesting because string theory proposes mirror symmetry, right? Propose In particular, there's a homological mirror symmetry which concern with this. Maybe I write it here. It says there's some mirror variety, and it doesn't need to be rough Fukaya category actually. Just some Fukaya category of the left side corresponding to some coherent shifts on some mirror variety. So this is the homological mirror conjecture. So of course, this is understanding the A side of this. And so what kind of computation we do here? So I should say what computation means here. So because I want to compute actually this graphical category. So I want to express it like perf of some endomorphism algebra of some Lagrangian. So L is some Lagrangian in W. And perf means perfect complexes. Some perfect complexes over this endomorphism algebra. This is the endomorphism algebra. Of L. Endomorphism algebra in the Fukaya category. So this gives you some infinite algebra, or you can even think it's DG algebra. You can deform infinite, you can find an equivalent DG algebra. So this is like a DG algebra, let's say. That means, in other words, like L split generates. Fukaya category. That statement is equivalent to what this. They have the same meaning. So writing it like perf of some DG algebra is my goal. Perf of DG algebra. So why? Actually, once you write it like this, it already tells you something about the mirror. So let's say this is perf A for some commutative algebra. Then the mirror is spec A. We take spec of it. And the coherent shifts on spec is just perf A. So if you get some commutative algebra here, you get the geometric mirror. But what if you get non-commutative one? That's the problem. Usually you get non-commutative one. Then, there are models for those, let's say, there can be still variety. Whose coherent shifts is that? And sometimes there are models for those like Landau-Ginzburg model. You can replace this with Landau-Ginzburg model with variety and with some potential. Yeah.
I don't actually follow this endomorphism algebra. Like, why does it have no higher multiplication?
It may have higher multiplication, but you can always make an infinite algebra, DG algebra, by unit embedding. You can unit embed it to its modules over that infinite algebra, and its image will be DG algebra. So this one way of doing this. Actually, there's more natural way of doing that also, which will appear in my talk, hopefully. But yeah, you can assume it's DG algebra for that reason. But let's say it's just DG algebra, non-commutative. Then mirror, you can just think the mirror as a perf A. This is derived non-commutative scheme. I mean, it's actually not geometric object, but there is a, you can do algebraic geometry on this kind of things. So perf A, there's an algebraic geometry on this kind of, you can define all smoothness, etc. All the concepts on this non-commutative space. So in short, you can think computation of this is the mirror. I mean, I'm just trying to amplify my result because I didn't have a geometric mirror. So that perf thing that I will find, you can consider a non-commutative mirror. But better result will be finding actual geometric realization of that non-commutative scheme, which I won't do that. I don't have such result, but there are results. So for this space, W, let's say P and Q, and luckily, and with the sensor here, they have, they had the Landau-Ginzburg model for mirror of this when Q is thinking, and n equals greater. So they have the mirror, the metric factorization. But there are some results there. Okay, so that's one motivation to deal with rough categories. Other, so one thing is, actually new part of my talk is understanding this compact categories, which is actually harder than to understand this one, because there are a lot of technology to understand this now, but we don't know much about compact category. All this full subcategory, but what part of it? I mean, if I know rough category, how can I get compact category nicely like a? So there is this claim. It's not actually, I won't say this is claim, but this is something that we want to be true. But sometimes maybe it's not true. Which is compact category is finite dimensional modules over that endomorphism algebra. Or let's first say rough category. You have a rough category, then it's finite dimensional modules over that, which is equivalent to finite dimensional modules over endomorphism algebra of L. So if you have that, that will be good. But this is true for cotangent bundles. And that's Nadler-Zaslow theorem. Of course, they present this theorem shift theoretically, but I don't want to enter too much in shift theory for the sake of time. But this thing you can think as microlocal sheaves actually on skeleton. It's not directly like that, but using some combination of some results, now we know this is the microlocal sheaf category, this data. From Ganadra partnership, the result actually, they show rough categories are rough microlocal sheaves. And from there, you can also get this is normal, usual microlocal sheaves. So does it equal to compact category? So we don't know that. But we know for cotangent bundles, not like Zaslow. Microlocal sheaves equal to compact category. So my goal is generalizing this to all plumbing space. One other goal. So, and this is partially done by Abuzet-Smith. Smith showed this for P and Q, where Q is 3. And the CIs, that Lagrangians that I initially, those CIs are simply connected. So they did for that case. What I say is I will show no condition needed for any of this. Plus all grading structure, etc. Any condition you put, it doesn't matter. It's true. But we prove partially what I said. So I will do some part of it as a claim. So maybe I should stop motivating because I didn't start. Maybe I just say what other motivation I have. Yeah.
Is there an example where that is not true?
This is not true. Yes. If you take rational homology balls, so the thing is you can make it true by playing with definition of this thing. So now initial definition is this is consisting of embedded Lagrangians. That's the natural definition because Fukaya category is also defined like that. I mean it's pretriangulate closure embedded Lagrangians. So but inverse Lagrangians comes as a result, then they can come to the category. But initially I don't start with this data. Here also let's say this embedded pretriangulate closure of embedded Lagrangians. Then if you take rational homology ball, studied by Lekili and Maindansky, so some certain rational homology balls have no embedded Lagrangians. So this category is automatically zero, but they have non-trivial Fukaya category, which I work on my thesis on this kind of things, and this is also non-trivial. So they are not equal, which means we need to add some inverse Lagrangian until we get this equality correct. In this setting also, sometimes I make for this to be true, I need to include inverse Lagrangians. But actually, it's better to define this with inverse Lagrangians. That's the moral of the story. We need to define it with inverse Lagrangians also. But in cotangent bundle case, we don't need to do that. It's embedded definition works. But I don't know where it's also fails with some inverse Lagrangians also. But anyway, you can always make this true, I feel, like, with some chosen Lagrangians. Okay, where am I now? So maybe just some other motivations are, once we understand this compact Fukaya category with this kind of finite dimension modules, you can actually study geometry of Lagrangians via module quiver representations. So that question of understanding geometry of Lagrangians inside Weissman manifold, like nearby Lagrangian conjecture, but we are generalizing to some not just cotangent bundle. So that kind of question also can be answered. And more other things also. Okay. I tell in the end if I have time. So now the results. Okay. What results I will talk about today? This is theorem 1. This is with Sangjin Lee. Me. This just computes this Fukaya category of this for P and Q. But for any Q and any CIs, doesn't matter. But I need to give some grading structure to this. I mean, to define Fukaya category, actually, there's a hidden extra data, which is, it's not the hidden, grading structure I need to put, which is not necessary when the H1 of the quiver is, H1 of the manifold is 0, but normally I need this kind of extra data. So that extra data is actually corresponding to saying that how this Lagrangian intersect as a graded Lagrangians. So I should actually decorate my picture further. I mean, this is defined enough to define Weierstrass manifold, but to talk about its Fukaya category, I need this extra choice of numbers, let's say, some integers. That tells that the intersection point has degree 1, because this is graded vector space, right? Their intersection. So what is the degree of their intersection? That I'm predefining their degree of intersection. And if this quiver is, there's no loop in the quiver, actually it doesn't matter. This data doesn't matter eventually. This is grading structure. So any grading structure you give me, any quiver, anything, then this is perf of some endomorphism algebra, and that endomorphism algebra corresponds to Ginzburg DG algebra in n case, n equals greater than equal to 3 case. So this is Ginzburg DG algebra with based local system, base, what was the name? Based loop space coefficients. So CIs in the example were S2, right? And there are R2 there also, but most of them were S2. So when it's S2, this coefficient became S2 minus a point. S2 minus a point is a disk. And then the loop space of disk is just whatever, like trivial thing. And this is chains on that loop space, which is also trivial. So this is just exactly Ginzburg DG algebra if I just use Sn. If this picture consists of Sn, but if it's not Sn, if I use other Lagrangians, then I need to compute this base loop space associated with those Lagrangians, and that kind of change this Ginzburg DG algebra. And this is derived preprojective multiplicative preprojective algebra. Again, same with blah 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 coefficients. Okay, so you can think this is Ginzburg DG algebra like additive preprojective algebra, but graded version of that. This is like and derived version of that, and this is like derived multiplicative preprojective algebra. So definition I want. So first of all, I will focus on this part today. This is the part I will focus. And second, definition I won't give fully now. I will give on an example. But idea is this: just how do you get that algebra from this quiver? So you have this quiver. Let's work on an example. Let's say my quiver is this. And let's focus on S2. Let's forget about base loop coefficients for now. Just when we have S2, we don't need to worry about coefficients. And let's say this is my diagram that tells me just two S2 intersecting according to this, and the one is the inverse. So this gives, you double this quiver, which means for each arrow, let's say x and y, you add a reverse arrow, and for each y, you add a reverse arrow, double that quiver, and for each vertex, you add a loop. Let's say this is vertex h, one more loop, hw. Let me just say, so since I'm writing, okay. And then, let's not make it S2, let's make it Sn to make the importance of clear. And then, this is some quiver actually. Let's make it graded quiver. X is X, because X is given by that initial data. That I already told what X is from that data. I say how they intersect. There's a number associated here, which is X, the grading of X. But I want this condition. So these are given by grading structure, and these are automatically determined, and I want to be this true. This is how you give grading, and HV, this extra new loops are given by 1 minus n, the degree, and the differentials are all 0, except the differential of HV is given by the adjacent arrows, like x and x star, right? So x star x. It's HW also. The y side, there's the x side, so it kind of commits them, not commits, identifies them by y. But there are two ways of composing this one. You can compose like this, or you can compose like this because it's loop. A minus sign, depending on is outgoing or incoming. So it just relays adjacent things like that. That's Ginzburg DG algebra. It's not algebra yet, it's just quiver, but then you take path algebra of this. Of that. Take path algebra of that, and you get a DG algebra. You can guess definition for any quiver from that picture. So far good. That's a statement. In multiplicative one, just the relation becomes e to the that. You can think like this. Becomes multiplicative instead of additive. Any question? That's it. Second theorem. So this is work in progress. This is already uploaded on arXiv. This is work in progress with Wonbo, Jeong, Sangjin Lee, and me. So it says, now this says about compact Fukaya category. And you define compact Fukaya category with definition also embedded and immersed. There's some immersed, could be more correct, but so you define Fukaya category like this, compact Lagrangians, exactly category of those Lagrangians, and then the the CIs, remember CIs, right? The things that, those things, the CIs generate Fukaya category of M. This is maybe part 1. With local system. And I should say under some, for some grading structures. Okay. Okay. Yeah, thanks. Here could be P and Q. Here could be P and Q. And I also said, forget to say n is greater than or equal to 3. Yeah, this is the second thing. Yes.
Yeah, there is one correction. Objects is considered QH3. They don't need the second condition. Yeah, it doesn't need to be.
Is it? Sorry. I mean, this is for this maybe true, but for that. Okay. Any question about statements or corrections or anything?
So nothing for n equals 2?
N equals 2, there may be something, but n equals 2 is harder because there are degree 0 loops in n equal 2 case. I'll see. I mean, actually, it became clear when I showed the argument, but yeah, for now, n equals 2. I expect this is not true for n equals 2, first of all, not true. But this may be true. This may be true. And first one also. Okay. I mean, this is work in progress, but for first one, I said some grading structure. This is not for some grading structure, by the way. This is true for all. This is a bit claimer. For other grading structure, we can still describe generators. More generators needed. But we can describe them geometrically. So there are some geometric Lagrangians, some global Lagrangians that you need to add in the generation family to generate this. But let me state like this. So now I will prove stuff, and I have 12 minutes. So what should I do? This more recent results. I tend to prove this one, theorem 2. And prove means just I will give some arguments. Let's discuss theorem 2. I already gave so many talks about theorem 1, so, and Sangjin also. So in theorem 2, so now theorem 2, of course, start from where theorem 1 left. So we have now knowledge of Fukaya category. So I'm assuming this is true. So before proving even theorem 2, I want to say something about how we can understand geometry, because this picture I think is nice. Then maybe I will tell something about the proof of theorem 2, then I will finish. So geometry from quiver representations via local to global method. So now let's first discuss this. What do I have? So I have Fukaya category of W. So let's from now on assume n is greater than or equal to 3. I have Fukaya category, and I have unit embedding. I have unit embedding of that into representation of itself, modulus over itself. And now I know this is Ginzburg DJ algebra, perf of Ginzburg DJ algebra. So I can write this is just infinite dimensional representations of Ginzburg DJ algebra. So it embeds that. That's first thing. And how does this unit embedding, okay? And let's say I take a compact Lagrangian. So L is compact Lagrangian. Then L sends, L goes what? Let's do concrete, concrete is better. So Q is again like this. Q is this. Let's even label them, V, W, E, and F. Vertex VW, this EF, and these points are representing Sn. Okay, if I have that quiver, which is that quiver over there, and I already say what the Ginzburg DJ algebra is, which is that thing over there. So basically, I need to represent that quiver there. I need to represent that. So for each vertex, I give, because field coefficient, just take a Floer homology, not the chain complex, Floer homology of L with CV. CV is the S2 at vertex V. So if you take any compact Lagrangian in your this plumbing space, so this is W is P and Q, by the way. From now on, it's always P and Q. For any compact Lagrangian plumbing space, the representation given by, you look at the Fourier homology between L and CV here. This gives you some vector space, graded vector space. And this, with other one, the CW, which is also S2, gives you another vector space. And you need to represent the arrows. Let's say this arrow X, right? Let's call it X again. X, Y. And there's a Y, and there is Y star. And there is a HV here, and there is HW here. Just representation of that quiver, this double quiver, okay? And those maps coming from the obvious map. Sorry, yeah. Yeah, I need to introduce that, sorry. So LV is Lagrangian dual to CV, which means I see here LV is the dual Lagrangian, which is like cotangent fiber on that. Okay. So basically, LV and LW are cotangent fibers at the respective place. These are cotangent fibers. From this, you see, of course, that intersection will be finite dimensional, right? Because it's intersection between compact Lagrangian and non-compact. So it should be finite dimensional. This is finite dimensional, this is finite dimensional. So this is inside finite dimensional modules over Ginzburg algebra. Compact Lagrangian's representation is finite dimensional because of this computation. And now I can give you this picture. So an example. I want to give you an example. Let's say now I want to take any module. Let's say take an element in mod FG, FD. So I know any compact Lagrangians give you finite dimension module. So now I'm taking finite dimension module, and how can I see this geometry if it's a geometric object? So an example is this. Let's say the module is K. So this K, that's K, and the arrows are 0 here. Let's say this is 1, this is 0. I mean, if this respect to gradings, assuming this is degree 0 graded, and this is degree 0, 0, 0. Like almost everything is 0, and there's this one there. So note that there are 3 arrows loops here, which all of them I represent by 0. Just I represent this by 1. So what is this, for example, in this picture? So first of all, what is this plumbing space, P and Q, skeleton of this, which is the This is Weinstein neighborhood of something, right? So this is, if you look at this quiver, one sphere, and this other sphere. Oops, I shouldn't. This quiver corresponds to this two Lagrangian intersecting. I'm looking at Weinstein neighborhood of these two Lagrangian. It's like two spheres, this immersed sphere, this embedded sphere. So I'm looking at Weinstein neighborhood of this, and this module should be some Lagrangian around this space. So what Lagrangian? So local to global method, I mean, what is this? So you cut this into pieces first. You cut it into standard pieces, let's say. So here, actually there is this. Okay. I chop it such that singularities, just I took neighborhood of singularities and the rest. Singularities are the where two disks are intersecting transversely. So of course, I have 2 minutes left. But in our paper, previous paper, we analyzed the symplectic geometry of this kind of spaces in two disks intersecting transversely. We analyzed the symplectic geometry, and more things to come. But we know how modules look. I mean, actually, it's work in progress. We know how modules look when they are restricted to there. So if you give me a module, I can maybe draw it. So let's say that module. How that module decompose on that space? So it decomposes like. So that K is actually for this part, right? So it's K here, K there. That K also. K here, K here, K here. That 0 is here 0. And that 1 and 0 is capturing the singularity. This is actually singularity data of this, that two morphs. And so we have some dictionary between quiver representations and the actual geometric phenomena. So using that dictionary, so I'm first decomposing. This is a categorical move. There's no geometry right now. This is this K, and there's monodromies here. They are 0 also. I mean, this 0 is also monodromy. I mean, higher monodromy here. There's this 0, 0, 0. And there's this K. There's also this K here. And this time, these two arrow capturing this singularity is about 0. Okay. So I chop it in pieces. I have modules in each piece. So how do I represent each piece geometrically? So in smooth parts, we know nearby Lagrangian conjecture holds K category sense, which means everything is 0 section with a local system. So these are just 0 section. They are itself. So my Lagrangian looks like exactly like the skeleton here and here. And this K same dimension, how many layers of I have? So here I have 3 geometric type of representation of this piece. One is already this. This is 1, this is 0. That corresponds to cylinder. Whenever I see this, it's cylinder. So this is a cylinder here. So when they are both 0, actually it's decomposable. It's actually, I can decompose it into K000 and 0000K. So I can decompose it. And each corresponds to a disk. This K part corresponds to this disk. That K corresponds to the other disk. So then what did I get? Actually, I get a sphere. This is a sphere. But this is an inverse sphere because these two touching here. So this corresponds to inverse sphere. So now you can think, can I do for any module represent? I mean, one way of proving what I said is this. I take any module representation, I draw it like geometric Lagrangian, then I'm done. But that doesn't work always. There are some pieces here which are bad. So the thing is, we can represent enough geometric objects via quiver representation. So there are some good amount of geometric objects we can represent via this quiver representation. And then once we have those geometric Lagrangians, the corresponding quiver representation generates whole finite geometric modules via just categorical arguments. So because we will have some collection of representations, and then the question is, can we generate all finite geometric model from that? And then there are some tricks which I had no time to show, but then you show they generate all Lagrangians. But again, this is also how you construct geometry of the Lagrangian from the quiver representation. Okay, I stop here. Thank you. This? So what was the question about that? And why this is 2 minus n? So you can think it this way. So when you need to understand this piece first. This piece itself is x, and it consists of these two vertex and 2 arrow, this piece. And no differential we have. And there are actually more stuff. So there is a monodromy here, right? There's a monodromy here. But it's like higher monodromy. If this is n is greater than 2, then there is a higher monodromy. Higher monodromy means you look at the representations of base loop space of Sn, not like pi 1 of Sn. Base loop space of Sn. So base loop space of Sn. So here this monodromy, an element of base loop space of Sn minus 1. Sorry, here this is Sn minus 1, because this is like disk. There is a disk here, and this is the boundary of this disk. And this boundary of disk should have a monodromy. And that monodromy is an element of, this should correspond to this. It's actually the image of this element. So there's a unique element here that gives you, that maps to this grading preserved wave. What is the grading of this z in Sn minus n? I mean, if you know the computation, this is given by, let's say, it's a kz. This degree of z is 2 minus n. I mean, you can confirm when n equals 2. When n equals 2 is S1. When S1, what is the degree? S1 is degree 0. Just invertible mark, right? So then it's not kz, z is invertible, right? So when you put n equals 2 is 0. But when you go S3, it's degree minus 1, degree minus 2, etc. So this, there is the monodromy here should be same degree as this thing, which is 2 minus n. But what are these x and x star do? Because I didn't show computation, it doesn't make any sense to you, but from the computation, you see that their role is capturing the singularity plus they give this monodromy as x star x. So this 2 gives a monodromy in the boundary, x star s, and this part they give monodromy x star. So therefore x star compose x and x star should be 2 minus n degree. That's why we have this degree condition on them. But x and x star can be anything, depending how you predefine grading structure. Yeah.
Any other question?
Okay. So can I ask you a question about the Tn of Q? Do you have some kind of relation, for example, topological relation between the meter and okay, right?
This?
Yeah. Do you have any kind of relation, generator relation, okay, or with the spatial equation relation?
And what kind of relation?
You have the generator. I have the
I have k.
right.
Okay.
Yes. Do you have between the 3 pieces? Do you have any recursion relation?
Like the relation. You like this kind of relation, you mean?
That's right. That's right.
Yeah, there is, but they're automatically satisfied.
I see.
So why? Because, for example, what is the relation? Relation is this, right? So in those examples, all h are 0. So this is 0. So y star y. Y correspond to these two, y and y star. Y is 0, y star is 0. This is 0, and this is 0. And x star, x is 1, but x star is 0, 1, 0, 0. So they are all 0. So 0 equals 0, they are satisfied. Yes, actually, I cannot represent just this picture.
Okay.
True. I should represent by looking at this, but which I implicitly did, but I didn't say yes. Yes, sir.
Okay, there's another thing. So you have the left hand genus 1, and then you have yeah.
This
Yeah, right.
this is, I don't see this like just genus 1. I see it like a, so yeah, there's this question. This is inverse torus or inverse sphere?
I see.
For me, inverse sphere. This
And
is
then next question I said topological relation, okay, with the genus. That's a topological recursion relation. In the case of the genus.
I could make a genus something also.
Okay.
Then, if I do that, if I put genus here, or if you do something like that, then you need to. So of course, this is a 2-dimensional example.
Yeah.
But let's assume we are in 2-dimension. So then you need to consider base loop space of torus.
Yeah.
Minus one point,
Yeah.
which is, what is that going from? I don't know, something. Then there is generators of this base loop space, the generator of homology of this base loop space, torus minus 1 point, and base loop space of torus minus 1 point. There are generators. So you need to put all generators here. So there are extra morphisms coming from, if you put torus there are extra morphisms coming here.
Okay.
And they also contribute this differential, someone. They contribute this differential.
Yes,
Yeah.
Thanks.
Yeah. So that's what I meant by coefficient with base loop space, base loop space coefficient in the first unit. So that means you need to add more arrows coming from those extra data, yeah. And you need to perturb this. Here.
P and Q.
This.
For subcategory of subcategory W2.
That's full and full subcategory of.
And is it proper?
It's proper, yes. This is proper.
Does it
This properness, I kind of, that's the argument for properness. So you say, I mean, you don't even need this. just home space are finite dimensional, right? Compact Lagrangians. So therefore it's proper. If you mean that kind of properness. Yeah, like categorical proper. Yeah, it's proper. Proper Calabi-Yau structure. Maybe Wonbo knows that stuff. Wonbo, you know? Proper Calabi. Proper Calabi-Yau. Oh, sorry. I thought I'm mistaken with cluster. Proper Calabi-Yau. Yes, this is proper Calabi-Yau. And Fukaya is the smooth Calabi-Yau. This is proper Calabi-Yau. This is smooth Calabi-Yau. It's always like that. It's nothing to do with Planck. This is.
Are they closer to each other?
Yes. In that grading condition, which I didn't even say. So if you give this grading condition, then they are Koszul dual. And this is from Lekile Econ have a Koszul duality criterion, and they show they are Koszul dual for quiver is 3, but we can extend it to again this any case. But you need simply connectedness condition. Your pieces should be simply connected. But you can have loops in your quiver, it's okay. Just there is some discrediting condition. If that's also satisfied, yes, they are Koszul dual. Fukaya category and Fukaya category are Koszul dual. Of course, that's also very specific to this case. Yeah.
What are some approximations of color division that are present?
Sorry? Yeah, this is n Calabi-Yau. That's what n. Both are n Calabi-Yau. This different proof, if you like, to prove Ginzburg DJ algebras are n Calabi-Yau, geometric proof of that. Because we know Fukaya categories are always smooth n Calabi-Yau. So since Fukaya category gives us Ginzburg DJ algebra, and with any grading, actually grading is important here. We can show without potential though. I didn't say that, but we can show any Ginzburg DJ algebra without potential is smooth n Calabi-Yau. By geometric, well, it's already known. So
There's no more question. Let's thank the speaker.